Hello, I am David W. Parker. This is Programming Today. I learned 3D Math Series, episode 12. We're going to be looking at more linear transformations today. Today we're going to be looking at rotation about an arbitrary axis in 3D. Now this is going to be pretty math heavy, but most of the math you have done before. It's just a lot of substitution and recalling previous episodes. So we'll go right in and I'll try to explain as best I can. But don't get overwhelmed by it. Just take a peek, look at it slowly, download the code, and you can really see exactly what's going on. So recall we're not translating right now, so the axis must go through the origin. This will make things easier for us. And we'll use the unit vector in to represent the axis. We're going to try to compute the matrix that rotates about that in by theta, so r of n theta. So we're going to have the vector r and then theta is equal to vector prime. So we're going to be trying to compute v prime given some matrix that we're going to be able to figure out what does that matrix look like. To simplify, we're going to solve the problem in the plane perpendicular to n. That'll make things a lot easier. So first recall you can split v into two different vectors, v perpendicular and v parallel. V parallel is parallel to n, obviously, so it won't be affected by the rotation. So due to that, we know that we have v prime is equal to v perpendicular plus v parallel prime. So you kind of have this graph, and I'll explain each of the bits real fast. You have the original n here. V parallel is the portion of v that is parallel to n, obviously, since they're going in the same direction. And you can see here's v perpendicular, w, v prime perpendicular, and v prime. If you look at v perpendicular here, you could see it's the value of n that's projected onto n, and so that is equal to v dot n times n to compute that. V perpendicular is the portion of v that's perpendicular to n. Obviously, that's this value right here. So here's the original v. We're rotating up to v prime, and then we're breaking it down into these pieces. So v perpendicular is equal to v minus v parallel, which is the result of the projection of v onto the plane perpendicular to n. W, this vector up here, is the vector perpendicular to both v prime and v parallel, and it has the exact same length as v perpendicular. And we compute that by rotating 90 degrees around n up, so we'll have w is equal to n times v perpendicular. So now we have v prime perpendicular up here, and as you recall in our 2D plane example back in the previous episode, we can see that that's just cosine theta v perpendicular plus sine theta of w. So you have each of these values, so sine w, theta w, plus cosine v perpendicular of theta. And that'll give you your v prime perpendicular. So now we have all the formulas we need, and we just do a lot of substitution, just base algebra. You can see we're going to substitute for v perpendicular and w here. So first of all, we have v perpendicular from the previous formula, nicely given already. Next up we have v perpendicular, and that's equal to v minus v parallel. And since you know that here, we can substitute that, and you're given this nice little formula. And finally, for w, we can see that w is equal to n times the v perpendicular, or cross v perpendicular. And you can see that here we can do the substitution for v perpendicular, and then again, we know this is going to be 0, so w is equal to n times v. Now we have v perpendicular and w, so we can substitute and find out the last value, which is v prime perpendicular. And substituting in for the v perpendicular as well as the w, we have this final formula here. So now that we have all of our, finishing that out, we have to go ahead and do the final substitution for v prime with that v perpendicular. So now we have our final formula here, given in terms of v and n and theta. So now we can compute each of the basis vectors p, q, and r, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1, plugging in p for the values of v and the same thing with an array of a vector for ins in x, y, and z. And so here's our total formula that we have. V prime is equal to cosine theta times p minus p dot n times n, etc., etc. So in each of these p values, we'll insert the column vectors just for display, making it nice and easy to read. And for the n's, we'll put in column vectors as well. So you can see this looks like quite a bit, but really it's just very simple math when we multiply this out. So this is slowly cleaning it up, and you can see this is just multiplying this p vector times the nx, and so that you're just given x times this vector here, and same thing over here. So we're just going to continue to clean this up until we get to the final result here. I'm not going to walk through each of these steps, but you can do the very simple math to get it yourself. I recommend just looking this over though and understanding how you're multiplying each value out at each step. Show your work, as they always said in high school. And then we're given this final result of p prime. You can do the exact same formulas with q and r with 0, 1, 0 and 0, 0, 1 and figure out what those are each going to be. I've done the work for you here, so this is your result for q, and this is your result for r, so that's r prime and q prime respectively. And finally, since you have p prime, q prime, and r prime, we have our matrix here, which are those values. So this top row here is p prime. Of course, we're showing them in column format here. They are row vectors equivalents here, so we have this row vector of r prime, this row vector of q prime, and the row vector of p prime. And this is the formula that you can use to rotate around a arbitrary plane theta degrees. So that's it for this episode. If you like what you saw, go ahead and subscribe, give me a like, share this on social media, and go to ProgrammingTIL.com and sign up for my newsletter. Have a great one. Thanks.